So in this lecture, we're going to look at how concentration affects the rate of a reaction and basically what processes we're going to use in order to establish rate laws for specific reactions. So before we get into the nitty-gritty details of the rate laws and how we establish the various components, I first want to discuss the reversibility of reactions. So if we look at the reaction example here, we basically have NO2 decomposing into NO and O2. Okay, and this would be looked at as our forward reaction. Okay, so basically our reactants going to products. However, the reality of reactions is that there are actually two processes occurring at the same time. So there is this forward reaction in which the decomposition is occurring. But there is also the reverse reaction which is occurring at the same time. Okay, so this process or this reaction actually has a reversible component to it. Okay, and we'll discuss this a little more in our next unit, but basically when you reach the point at which the forward reaction rate and the reverse reaction rate are the same, there's not going to be a net change in the concentration of reactants or products. So basically overall, the concentration of reactants and products will remain constant. And this is called chemical equilibrium. Because this fact exists, we have to make a few assumptions and we have to make a few points of observation in our rate law determination. Okay, so basically what that means is that when we're looking at writing rate laws and things of that sort, we're going to usually study our reactions very soon after reactants are added together. And the reason why is because at that point we know that in the whole entire situation, the reverse reaction is less likely to make any contribution. So most of the studies that we're doing in terms of establishing rates and basically how we go about figuring that out will deal with the reactants being mixed and basically the soon after analyses of concentrations and things of that sort. So now that we've discussed the reversibility of the reactants, let's go ahead and move on to what we're actually trying to cover for this lecture. So general rate laws are basically rate laws that we write that basically indicate the rate of a specific reaction with respect to the concentration of only the reactant concentrations. And remember, as we just discussed, there is the reversible component to the reactions, but we will not be paying attention to those because basically if we're looking at the beginning of a reaction or very soon after reactants are mixed, we anticipate the reverse reaction being negligible. So how does a rate law get written for a specific reaction? So if we take this generic reaction here, okay, the rate law is going to be written as follows. So the rate of this specific reaction here is going to be equal to K, which is a rate constant, okay, and that's going to be variable with temperature. The concentration of my reactant A to some power, the concentration of my reactant B to some power, and these all combined give me my overall rate law. Okay, now M and N are called the order, and we're going to discuss how we figure those out and basically how they affect the rate of the reaction in a little bit. But for now, we just need to understand and accept that M and N are experimentally determined. Okay, so we actually have to run reactions. Remember that in our rate laws, we're not going to include products because we are ignoring the reverse reaction. Okay, and as I said earlier, your rate constant K, that's going to be variable with temperature. So anytime you're carrying out a reaction involving the establishment of rate laws, you want to keep your temperature constant. So let's go ahead and let's look at the rate law for a specific reaction. So let's go ahead and look at the decomposition of NO2 to NO and O2. So basically when we write our rate law for this specific reaction, okay, first of all, remember we are going to have a rate constant. Okay, we're going to have the concentration of our reactant. So in this case, we only have one reactant, which is NO2. So we have our bracketed NO2 in our rate law. And then remember, we're going to have some exponential value which indicates the order of the reaction. Okay, so at this point we have written our generic rate law. Okay, and we have some information, or at least we have a generic example that's been given here, but obviously we're missing a few pieces. Okay, and one of those pieces is obviously the value of our exponential our exponent. Okay, remember that's determined experimentally, and we'll get back to that in a minute. Notice we've only used reactants in our rate law. Okay, and obviously we have K being included in the rate law above. So now let's go and look at some more in-depth details about the rate law. So determining basically what the rate law is going to be, the completed rate law is going to be, will require exponents being solved for. Okay, and remember we said those are determined experimentally. So, but before we figure out how to determine those experimentally, why don't we go ahead and take a look at what they actually mean with respect to affecting the rate of the reaction. Okay, so remember we talked about M and N being the order of the reaction. Okay, so what you need to understand about the exponents is that they dictate the overall reaction order. Okay, and we're going to talk about how that affects the rate specifically, but before we move into that, let's talk about the vocabulary. Okay, so if I have an exponent of m equals 1 for this rate law here, what that means is that we would say that the reaction rate, okay, or the reaction is first order with respect to A. Okay, if our exponent n is equal to 1, we would say that the reaction is first order with respect to B. Okay, now the reaction order overall is going to be the sum of those exponents. So in this case, 1 plus 1 gives us 2. Okay, so that would be second order overall. So why do we care what order reaction or what order reaction we have, or what the order is with respect to different reactants? What's the point? Who cares? Okay, well, why we care will be explained here. So your exponents are going to show how the rate is affected by the concentration of each of the individual reactants. Okay, so if I take this rate law here, okay, and let's say that I find out that my M value is equal to 1. Okay, so what that means is this is what my rate law would look like. So what this means is whatever concentration for A I plug in, that's going to be the rate that I get. Okay, so if I start with a concentration of 1, okay, I will have a specific rate. If I double that concentration, right, my reaction rate is going to be doubled. If I triple it, it's going to be tripled, etc. It's kind of a direct relationship in that respect. Now, if I take that same generic rate law that we see here, okay, and I figure out experimentally that my order, or my M value, is 2. Okay, well, when I go ahead and I come back here and I plug in my concentration values, what I'm going to see is that whatever value I start with, right, if I change the concentration, I'm not going to get a doubling anymore. At that point, I'm going to get a quadrupling. So if I look at this, if I start with a a concentration of A equal to 1, okay, I'm going to have a specific rate value. If I double it, right, if I double that concentration, my reaction rate is going to quadruple. Okay, so basically this exponent is going to indicate how the concentration of the reactant is going to affect the overall rate of the reaction. Okay, so obviously the exponents are pretty important in terms of figuring out, what's going to affect the rate most drastically. So for a specific chemical reaction, we can basically get some information from the data associated with the concentration changes over time. Okay, so the first thing that we would do is we would look at the chemical reaction that we're actually carrying out, and we would write our generic rate law. Okay, so for this reaction here, our generic rate law is going to look like so. Okay, so obviously we want to figure out what our N value is, and we can get that information from our data. Okay, so in this specific situation, what we would do is we would take our concentration and time data and we would graph it like we see here. Okay, and then what we would do is we would take that data and basically compare instantaneous rates to one another. Okay, so basically we would select a concentration value early on into the reaction. And the reason we do that is because, at that point in time, the reverse reaction is negligible. And so it's one of the best times to take our instantaneous rate. And then when we get to basically half of that concentration, we then take a line tangent to those points on the curve and subsequently take our rise over run and find the rates at both of these points. Okay, so remember the concentration here and here, okay, are basically related by a factor of 2. So the concentration here is the original concentration. This is the halfway point. Okay, so if this reaction is first order, we would expect that having the concentration of our reactant would give us a rate change of half of the rate we saw from the original value we measured. Okay, so in this case, what we actually see is a halving of the rate. Okay, so in that case, or in that situation, we can therefore ascertain that our n value is subsequently equal to 1. Why? Because a first order rate law is going to, double in rate if you double the concentration, or triple in rate if you triple the concentration, or halve in rate if you halve the concentration of your reactant. Okay, so this is one way to approach it. Obviously, graphing is not the easiest approach to deal with, but it is a means to actually obtaining the rate law and the order of your reaction. Okay, so something I want you guys to notice from the rate law that we just calculated on this previous slide is that our rate law is first order, right? Okay, so we figured that out. Now, if you look at this and you compare it to, say, the coefficient that's in front of our N2O5, okay, you notice that they aren't the same values. Okay, so what I want to point out here is that your rate law exponents, or your orders, must be established experimentally. Okay, they do not come from coefficients. They are not values that you can obtain from the balanced equation. You must have experimental data that involves concentration and time changes in order to get there. Okay, and I just want to re-emphasize as well that for first order reactions, okay, whatever change in concentration we have, that's going to directly affect the rate. So as I said, if you double it, the rate's going to double. If you have it, the rate's going to halve. Okay, so basically, you need your n values and m values, those exponents, to be established experimentally. And first order reactions are directly related to the concentration of the reactants. Okay, so another way of finding our rate laws, okay, our specific rate laws and their subsequent exponents, is through the method of initial rates. Okay, so first of all, what do I mean by an initial rate? Okay, basically that's the instantaneous rate just after t equals 0. Okay, so really before the initial concentrations of reactants have changed and before really there's any opportunity for a reverse reaction to occur. So if we go ahead and look at this specific example of an equation or reaction type, we would write our general rate law as follows. Notice, once again, you got your K value, okay, your rate constant, you got your concentration of your two reactants, okay, and you have your M and N values for your orders. Now, of course, we have to figure out M and N, and that's where this method of initial rates comes from. Okay, so first thing you're going to need is you're going to need experimental data, okay, associated with the concentrations of both of your reactants and the subsequent rates established at that initial point. So experiment 1, okay, your initial rate is going to be 1.35 times 10 to the negative 7, okay, m over s. All right, and you have that initial rate for different conditions associated with the concentrations of the two reactants. Okay, so in experiment 1, we have a concentration of 0.1 and 0.005 for each of the reactants, NH4 plus and NO2 minus respectively. Okay, notice we have a different set of concentration conditions and another set of concentration conditions. Okay, and then you have their corresponding rates. Now, what we then are going to do is obviously write our rate law for a reaction. Okay, so our general rate law for the specific reaction that we're looking at here, okay, is as such. Now, in order to figure out our N and M values, we are going to compare the initial rates, okay, of two of the experimental data sets. Okay, so in this case, we're taking and comparing rate 2 and rate 1. And one of the reasons why we're doing that is because we have our concentration of NH4 plus being the same in both experiment 1 and 2, while we have the concentration of NO2 minus being variable in this case for experiments 1 and 2. So it allows us to have a point of comparison so that we can subsequently calculate our M value associated with NO2. So what does that mean we're going to do? Okay, well, we're going to plug in the rate laws and both our rate and concentrations at each experimental set. So really, another way to look at this is rate 2 over rate 1, okay, is going to be equal to K, excuse me, concentration of NH4 plus to the N value, right? And then concentration of NO2 minus to my M value, okay? And that's going to be over the same thing, NH4 plus, because obviously we're dealing with the same reaction type, okay? Right? And then what we do is we plug in the subsequent numbers. So notice for rate 2, we're plugging in the 2.7 times 10 to the negative 7th. Okay, and for rate 1, we are plugging in the 1.35 times 10 to the negative 7. So that's being plugged in here and here. Okay, we have our K's. Now we're plugging in the concentration of our NH4 plus. Right, so NH4 plus, the 0.1 and the 0.1 respectively. Okay, and then for our NO2, okay, I'm plugging in my concentration of NO2 in experimental, the experimental data set from experiment 2, plugging that in, okay, plugging the value in from experimental data set 1, right, and you subsequently have this setup. Okay, now, so we're going to obviously do some mathematical operations. And so what we're going to see here is when we divide our 2.7 times 10 to the negative 7th by 1.35 times 10 to the negative 7th, okay, that's going to give us our 2. And that's going to be equal to, okay, so K and K are not going to be included because they cancel out. Obviously, our N values and the subsequent concentrations here are going to cancel out because they're in a one-to-one setup. Okay, so what we're left with is our 2, okay, and our variables that are associated with M. Okay, so once you have that, you go ahead and divide the 0.01 by the 0.005. Okay, and that's going to give you 2. So 2 to the nth power. Okay, 2 to nth power is equal to 2. So in order for that to be true, M has to be 1. Okay, so in this case, I have now found out that M equals 1. So if I go back and rewrite my rate law, I now know that my M value is actually a 1. Okay, and you can write it as 1, or you can just leave it blank without the variable, and the assumption there is that you have a 1. Okay, so now that we've figured out our M value, we have to repeat this process in order to calculate and figure out our N value. Okay, so in the same way that we selected data and basically are comparing two rates, we're going to do the exact same thing, but in this case now we want to find a data set preferably that has NO2 being held constant, because remember that's the one that we need to basically cross out. Okay, we already know that M is equal to 1, so we really don't want to worry about that. So we go ahead and we look at our data set. Okay, notice that our NO2s here have constant concentrations, and we have variable concentrations here. So that'll allow us to find the appropriate exponent. Okay, so just like we did last time, we're going to compare the two rates. Okay, we plug in the instantaneous rate, or the initial rates that are being recorded from the reaction. Okay, we plug in our concentration values into our rate laws, right, from the data table. The ones that overlap, so my concentrations here and my M values, as well as our Ks, they're going to cancel each other out. Okay, when we divide our 5.40 times 10 to the negative 7 by our 2.7 times 10 to the negative 7, okay, that's going to give us 2. Okay, and then we end up with our 0.2 to the nth divided by our 0.1 to the nth. We divide those into each other, and that gives us our situation here. Now 2 is equal to 2.0 to the nth power. Okay, so in order for that to be true, our n needs to be equal to 1. Okay, so we know that our m value that we calculated on our last slide is equal to 1, and we now know that our n value is also equal to 1 based on our method of initial rates that we just carried out. Okay, so this reaction now can be described in several different ways. So the rate of this reaction is first order with respect to our NH4 plus, okay, and it's also first order with respect to our NO2 minus, and we know that because our exponents are there. Now, our overall order of our reaction is going to be related to the sum of those exponents. So in order to get the overall reaction order, we're going to add the exponents, both n and m, okay? And if there were additional reactants, then obviously we would have other variables, okay, O, P, or whatever you want to use. Okay, so for the rate law that we just calculated, the overall reaction order is 2. Okay, now that we have this specific rate law and we know our order of the reaction with respect to each of the reactants, we can subsequently use the data that we have from the initial rates tables to figure out what our K is. Okay, so what are we going to do? We're going to take this expression, right? Okay, we're going to plug in our rates from one of the data table data sets. So in this case, we collected or are going to use experiment 1. We plug in our rate. Okay, K we do not know. We know our concentration of NH4 plus. We know that it's to the first order. Okay, we know our concentration of NO2 minus, and we know that it also is the first order. We carry out the math and solve for K, and we subsequently get 2.7 times 10 to the negative 4th as our rate constant. Now the units for your rate constant are going to depend on obviously both the units and the powers or the orders of your exponents. Okay, so in this situation, okay, I have molarity to the first power times molarity to the first power. My rate is in molarity per second. Okay, so really what I have here in terms of my units is molarity per second is equal to molarity squared. Okay, right, so when I go ahead and try to isolate K by dividing it out, okay, what I'm actually getting there is m over s times the reciprocal, or 1 over m squared. Okay, so in that situation, molarity and molarity cancel. Okay, so I'm left with 1 over seconds times molarity. Okay, or another way to express this is by showing that they are to the minus 1 power, indicating that they're below that 1 in terms of units. Okay, so different rate constants for different ordered reactions are obviously going to have different units. So you want to make sure that you're comfortable with identifying the units properly and basically that you're able to give the units that correspond to that specific reaction type. Okay, and another thing I want to mention is, generally speaking, you can kind of judge the speed of your reaction or the rate of your reaction with respect to how large the K values are. So if you have a value of like 10 to the negative 9 or larger, it's a very fast reaction. If you have a value of 10 or below, you have a really slow reaction. Okay, and anything in between is going to obviously be somewhere in between in terms of medium speed, I guess. So basically, you need to get, in order to get a specific rate law, okay, you need to figure out your exponents. So after you've written your generic rate law with your exponents, you need to then find your exponential values using the method of initial rates. Once you use the method of initial rates to figure out those values, you can then take the data and plug in your concentration values and the rates for that experimental data and subsequently solve for your rate constant. Remember, your rate constant is going to be dictated by the type of order of reaction you have, and its units will obviously match those units that are appropriate to that type of reaction.